Hello and welcome to Algorithm video series. Today in this tutorial we'll talk about first occurrence problem, last occurrence problem, count of occurrence problem, lower bound problem and upper bound problem. Here we can calculate count of occurrence using first and last occurrence. Also we can calculate count using lower bound and upper bound index. First we'll talk about first occurrence problem. Here is the problem statement. Here, input of our program is a sorted list of numbers with duplicate elements and a target element, and output is index of the first occurrence of that given target element. For example, here we can see a sorted list of numbers with duplicate elements, right? Here target is 30 and index of first occurrence of 30 is 2 here. That's why output is 2. First occurrence in a list of numbers means the position or index where a particular number appears for the very first time in the list. For example, in this list, if I want to find the first occurrence of 10, then that is at index 0. It appears only once. So here first occurrence and last occurrence is same, that is at index 0. But if I take element as 40, 40 appears at index 3 and 4, right? So if we talk about first occurrence of 40 in this list, that is at index 3. Here last index of 40 is at index 4. First occurrence is the index or position where a particular number appears for the very first time in the list of numbers. To find the index of first occurrence of the given target element, we can use linear search algorithm. As we know, in linear search, we'll search in sequential order, right? That's why in linear search, we'll get the index of the first occurrence of the target element easily. For example, here we can see that. But here in the problem statement, it is mentioned that the input is sorted list of numbers with duplicate elements, right? So when we are using sorted list, it is better to use binary search algorithm to find the target element and also to find the first occurrence of the target element. But here we can't use normal binary search algorithm because in normal binary search, as soon as we find the target, we'll return the index, right? But here the element may appear multiple times because duplicate elements are allowed here and we want to find the first position. So we need to modify binary search algorithm. So what we need to do is, first we need to find the middle element. Then compare the middle element with the target element. If it is equal, then don't return the index like we do in the normal binary search. Here, we need to store that index in case it turns out to be first occurrence of that target element. And we need to continue search in the left side to see if there is earlier one. If find another target on left, update the result. If not, mid remains the result. When middle element is our target element, what we need to do is first we need to store that index because it can be the first occurrence of that target element. Next, we need to continue search in the left side to see if there is earlier one. If we find another target in the left side, then we need to update the result, that is index. If not, mid remains our result. And next, if mid element is not equal to target element, then we need to check whether target is greater than middle element. If it is true, then we need to search in the right side. Otherwise, we need to search in the left side, like normal binary search. What is the difference between normal binary search and modified binary search? Here you can see, when middle element becomes equal to target element, in the normal binary search, we'll return its index and we are done. But in the modified binary search, we are searching for the first occurrence of the target element. When the middle element equals to the target, there are two possibilities. First one is, it is the first occurrence of the target element in the list. And the second possibility is, it is not the first occurrence of the target element in the list. That means the same number appears earlier. So we have to look to the left because here input is a sorted list with duplicate elements. That's why in the modified binary search algorithm, when target becomes equal to middle element, we'll store the index first and next we'll continue search in the left side. Here, duplicate elements are allowed. Finding target once doesn't mean it is the first time it appears. So that's why store the index of the middle element and keep searching in the left half to see the same value appears earlier. Next, let's take an example. Alright, here we have list of numbers, sorted list of numbers, and these are all the index. Okay, first step is we need to find the middle element. Here low plus high truncated division 2. So we'll get middle as 3, right? So this is our middle element. Then compare the middle element with the target. So let's take target as 30. So middle element is equal to target. Here it is true. In this condition, 30 is equal to 30. So target is found. Now what we need to do? We need to store the index of this middle element because it can be the first occurrence of our target element. So let's take a variable and we'll store its index. Next, we need to continue search in the left side. So here to search in the left side, I need to take high equal to mid minus 1. So this is our search area now. Again find the middle element. 0 plus 2 truncated division 2. So middle is 1. So this is our middle. Compare middle with the target element, that is 20 is equal to 30. Here it is false, right? Then compare whether the target element is greater than the middle element. Here yes, 20 is less than 30. So 30 is greater than 20. So what we need to do? We need to search in the right side of the middle element. So now low becomes mid plus 1. We'll do the same thing with the normal binary search, right? Now this is our low. Next, again find the middle element. Now this is our search area. So again find the middle element. 2 plus 2 truncated division 2. So we'll get 2 as the middle element. So this will become our middle element. Then compare the middle element with the target element. Here 30 is equal to 30. True. So when it is true, that means we found another target element. So what we need to do is we need to update this variable now. We need to store this index. Here index is 2. So answer is 2. This variable will store the index of the first occurrence of the target element. So now update this. So here answer is 2. Next, what we need to do? We need to search in the left side. So I'll take high equal to mid minus 1. Here when high equal to mid minus 1, high becomes 1. Here low is greater than high. So now we need to stop the binary search. Here this variable holds the result, that is the index of first occurrence of the target element. Okay, let's take another example. First step, find the middle element. 7 truncated division 2, so we'll get 3, that is the middle element. Then compare middle with the target element. Let's take target as 22. Compare the middle element with target. Here it is true. So what we need to do? We need to store this index and we need to search in the left side. We need to check whether 22 is already present in the left side or not. So here to search in the left side, I need to take high equal to mid minus 1. Again find the middle element. Low plus high truncated division 2. So we'll get middle as 1. So this is our middle element. Compare middle element with the target element. 11 equal to 22. No, it is not. 11 is actually less than 22. So we need to search in the right side of the middle element. So low becomes this, mid plus 1. Now again we need to find the middle element. So here 2 plus 2 truncated division 2. So we'll get this as the middle element. Compare this middle element with the target element. 22 is equal to 22. True. It is true. So now we found another target element. So we need to update this index. We need to store this index now. Here again we need to check in the left side. High becomes mid minus 1. But here low is greater than high. So we need to stop the binary search. So answer is 2. Let's take another example. Here this is a list of numbers. Target is 111. And initially low is this, high is this. We need to find the middle element. So low plus high truncated division 2. So we'll get 3. So this is our middle element. Then compare the middle element with the target element. Here it is not equal and target is less than middle element. So when target is less than middle element, we need to search in the left area, right? So high becomes mid minus 1. Now high is mid minus 1. Here we need to repeat the same thing. We need to find the middle element. 0 plus 2 truncated division 2. We'll get this as our middle element. Compare the middle element with the target element. Here target is 111 and middle element is 111. It is equal. So we found our target. Now what we need to do is we need to first save that index because it can be our possible answer. Then we need to search in the left side. So to search in the left side, I'll take high as mid minus 1. So now high will point to this. Okay. Now we need to find the middle element. Low plus high truncated division 2. So we'll get this as middle element. Compare the middle element with the target element. Here 111 is equal to 111. So here we found another target element and we need to store this index now because this is the first occurrence of 111 now. So save that index. Next, we need to search in the left area. To search in the left side, I'll take high as mid minus 1. Now high point to minus 1. Now here you can see low becomes greater than high. So we need to stop binary search now. The first occurrence of target element, that is 111, is 0th index. Let's take another example. Here target is 444. So first find the middle element. So this is the middle element. Compare the middle element with the target. 222 is equal to 444. No, it is not. And here target is greater than the middle element. We need to search in the right side. So low becomes mid plus 1. This is our search area. Now find the middle element here in this search area. 4 plus 7, that is 11. 11 truncated division 2. So we'll get 5. This is middle element. Compare the element with the target element. Yes, it is true. Middle element is 444 and target element is also 444. So it is equal. So we need to store that index here. It can be the first occurrence of our target element. So store that index and search in the left side. Right? So here high becomes mid minus 1. So now high will point to this. Now this is our search area. Find the middle element. So we'll get this as mid. Compare middle element with the target element now. Here middle element is not equal to target element. So what we need to do? When it is not equal, then compare whether middle element is less than target element. Yes, middle element is less than target element. We need to search in the right side. So low becomes mid plus 1. But here we can see low is greater than high now. So in binary search, when low becomes greater than high, we need to stop. So here we need to stop and here our output is 5. That is the first occurrence of the target element, that is 444. Okay. So let's write the program. As I said, we can use linear search algorithm to find the first occurrence of the target element. No need to do any changes to linear search algorithm. Just use linear search algorithm. How many elements? Let's take 5. And here because problem statement says that it is a sorted list of numbers with duplicate elements, I'll enter elements like this. Then I'll enter target element as 30. Then we'll get index 2. Because linear search algorithms search in the sequential order, we'll get the first occurrence easily. So no need to modify the linear search algorithm. So next, let's talk about binary search algorithm. This is the normal binary search algorithm. When target becomes equal to middle element, we'll return its index. So let's save this and execute this and we'll see whether it works for the sorted list with the duplicate elements to find the first occurrence of the target element. So let's enter 5. Alright. So now I'll enter 20 as my target element. So we'll get index as 2. But actually we need output as 1 because the first occurrence of 20 is at index 1. That's why I said normal binary search doesn't work here. Because when target is found, it will return its index. But here we need to search for the first occurrence of the target element, right? So here we need to modify this binary search algorithm. We need to change this part. When target is equal to the middle element, what we need to do is we need to store that index first. For that, let's take a variable. Initially, I'll take its value as -1. And here, when target is equal to middle element, then store that index. Then continue search in the left side. For that, I'll take high equal to mid -1, right? Next here, we need to return answer here. Here, this algorithm returns the index of first occurrence of the target element if target is present in the given list of numbers. If target is not present, then we'll return -1. So that's why initially I'll take answer equal to -1. If target is present here, then it will return the index of first occurrence of that element. Otherwise, it will return -1. Okay, now we are done. Let's save this and execute this. Let's enter 6. I'll enter 40. 40 is found at index 3. That is the first occurrence. Alright, so this is how we can find the first occurrence of the target element in the given sorted list of numbers with duplicate values. Okay, so this is about first occurrence problem. Next, let's talk about last occurrence problem. Here is the problem statement. So input of our program is a sorted list with duplicate elements and a target element. Output is last occurrence of the target element. For an example, here we have a sorted list. Our target is 30. Then our output is index 3, last occurrence of 30. Here 0, 1, 2, 3. In this list, this is the last occurrence of 30. Its index is 3, so output is 3. If an element appears multiple times in a sorted list, the last occurrence is the rightmost position of that element. And the first occurrence is the leftmost position of that element. And if an element appears only once in the sorted list, then that is the first and last occurrence of that element. Here in this example, if I take target as 30, then last occurrence of 30 is index 4. The first occurrence is index 2. If I take target as 20, it appears only once. So this is the first occurrence, and also this is the last occurrence of this element. Okay, so now how to find the last occurrence of the given target element in the sorted list containing duplicate elements. For this, I'll use binary search algorithm. But normal binary search algorithm doesn't work here, because in the normal binary search algorithm, we'll search for the target. Once it is found, we'll return its index and the message target is found. But here we want last occurrence of the target. Target can appear multiple times and we want the last occurrence of the target. For an example, here if I take target as 30 and if I apply normal binary search algorithm to find the last occurrence. So in the binary search algorithm, I'll take this as low, this as high. This is our search area now. So we'll find the middle element first. So we'll get 3 as our middle element. Then we'll compare the target element with the middle element. Here 30 is equal to 30. I'll take target also 30. Here middle element is equal to target element. So what our binary search algorithm will do? It will return its index, right? What is its index? 3. So it will return answer as 3. But actually here last occurrence of 30 is at index 4. So we can't use normal binary search to find the last occurrence of the given target element. So what to do? We need to modify our binary search algorithm. First, we need to find the middle element like we do in the normal binary search algorithm. Then we'll compare the middle element with the target element. Next, if middle element is equal to target element, in the normal binary search algorithm, we'll return the index. But here, in the modified version, what we need to do is, when middle element is equal to target element, we need to first store that index, because it can be our possible answer. It can be the last occurrence of that target element. Okay, so first we need to store that index. Next, we need to continue search in the right side to see if element appears again. Because here we want last occurrence, we need to search in the right side of the middle element. If we find another target on the right side, then we need to update our result, that is the index. Initially, we'll store the index of the middle element. If we find another target, then we need to update that. If not, if we didn't find target element on the right side, then that means middle element is the last occurrence of the target element. So we'll return that index. So mid remains our result. Then here, if middle element is not equal to target element, then what? If middle element is less than the target element, then we'll search in the right side, like we do in the normal binary search. If it is false, then we'll search in the left side, like we do in the normal binary search. Here, we need to modify this scenario. When middle element is equal to target element, then we need to store that index and we need to continue search in the right side of the middle element. So here we can see the difference between normal binary search and modified binary search. If you want to find the first occurrence of the target element, then we need to store the index of the middle element and we need to search in the left side. Here we want to find the last occurrence of the target element. So when target element is equal to middle element, we need to store that index and we need to continue search in the right side of the middle element. That is the difference between the first occurrence and last occurrence. Next, let's take few examples. Let's take target as 30. We want to find the last occurrence. So let's find the middle element. Low plus high truncated division 2. So we'll get index as 3. This is our middle element. Then compare 30 with target 30. It is true. Target is equal to middle element now. Now what we need to do? To find the last occurrence, first I need to store the index of the middle element. Because target is equal to middle element, I need to store the index. And now search in the right side of the middle element. For that, I'll take low equal to mid plus 1. So now this is our search area, right? Find the middle element now. So 4 plus 6 truncated division 2. So we'll get 5. And this is our middle element. Compare middle element with the target. 40 is equal to 30. No, it is not. Actually, middle element is greater than target element. So we need to search in the left side, right? High becomes mid minus 1 now. So high will point to here. Then we'll find the middle. So we'll get this as middle. Compare the middle element with the target element. It is equal. When target is equal to middle element, what we need to do? We need to store that index in this variable, right? So here now, answer is 4. Update this variable. Now, we need to search in the right side. When target is equal to middle element, we need to store that index. We need to search in the right side. To search in the right side, we need to take low equal to mid plus 1. So now low becomes this one. But here you can see low is greater than high now, right? When low is greater than high, we need to stop binary search. So stop the search. And this variable will hold answer now, that is index 4. This is the last occurrence of our target element, that is 30. Let's take another example. Let's take target as 444. First find the middle element. 0 plus 7 truncated division 2. So we'll get 3. So this is our middle element. Compare the middle element with the target element. Middle element is not equal to target element. Then check whether target is greater than middle element. Yes, here target is greater than middle element. So when target is greater than middle element, this is a search area now. So again find the middle element. 4 plus 7, 11, 11 truncated division 2, 5. So we'll get this as our middle element. Compare the middle element with the target element. Yes, here target is equal to middle element. So store that index and search in the right side of the middle element. So low becomes mid plus 1. Now this is a search area. Again find the middle element. Low plus high truncated division 2, 6 plus 7, 13 truncated division 2. So we'll get 6. This is our middle element. Compare the middle element with the target element. Yes, it is true. So store its index and search in the right side. So here low becomes mid plus 1. So now this is our low and high. Find middle element and compare middle element with the target element. It is true. Then what we need to do? We need to update answer now. Answer is 7. Then we need to search in the right side of the middle element. So low becomes mid plus 1. Low is actually 8 now. Now low is greater than high. So we need to stop binary search. So this is our answer. That is 7. The last occurrence of 444 is at index 7. let's take 1 1 1. Compare the middle element with the target element. Target is less than middle element. So search in the left side. High becomes mid minus 1. Now find the middle element again. Compare the middle element with the target. It is true. So store its index. Then search in the right side of the middle element. So here low becomes mid plus 1. So here now this is a search area. Find the middle element. Low plus high truncated division 2. So we'll get this as middle element. Compare the middle element with the target element. It is equal. So we need to store its index. So 2. And we need to search in the right side. So now to search in the right side, low becomes mid plus 1. Now low becomes 3. But here low is greater than high now. So we need to stop the search. Answer is 2. Next, let's write the program. Here we have a normal binary search algorithm. So let's modify this binary search algorithm to find the last occurrence of the target element. So for that, we need to modify this section. When middle element becomes target element, we need to store that index. For that, let's take a variable. Initially, we'll take its value as minus 1. Then here, instead of returning value, answer equal to mid, we'll store that index and we need to search in the right side of the middle element. To search in the right side, we need to take low equal to mid plus 1. And here, we need to return answer. If target is found, then this function will return the last occurrence of the target element. If target is not found, then it will return minus 1. That's why initially I took answer as minus 1. If target element is not found, then it will return minus 1. So no need to change anything else. Let's save this and execute this. Number of elements in the list, let's take 6. Enter the numbers in the ascending order, a sorted list. Let's enter target as last occurrence is index 2. Last index is 4. Okay, so this is how we can find the last occurrence of the target element in the sorted list containing duplicate elements using binary search algorithm. Okay, so this is about last occurrence problem. Next, using first occurrence and last occurrence, we can calculate count of occurrence. That is how many times target appears in the given list of numbers. So next, let's talk about count of occurrence problem. Here is the problem statement. Given a sorted list containing duplicate elements and a target value, return the number of times the target appears in the list. Our input is a sorted list containing duplicate elements and a target value. Output is number of times the target appears in the list. For an example, here we have a sorted list with elements 10, 20, 30, 30, 30 and 30. Now our target is 30. Then we'll get output as 4. 30 appears 4 times in this list. 1, 2, 3, 4. Then if I take target as 10, output is 1. It appears only once. That's why output is 1. And we can solve this problem using different techniques. Here we'll talk about linear search method and binary search method. In linear search algorithm, we'll search for the target element in sequential order, right? Initially, we'll compare the target element with the first element of the list. Here, if I compare 10 with 30, 10 is equal to 30. No. Then we'll compare the next value with the target element. Here, 20 is equal to 30. No. Then let's compare next element of the list with the target element. 30 is equal to 30. True. So what I'll do is I'll take a variable, for example count, and I'll take count as 1 now. Because here target is found, I'll take count as 1. In the normal linear search, once the target is found, we'll return its index and we'll stop. But here we want to find how many times the target appears in the given list. So what I'll do is I'll continue searching and I'll go to the next element. Here next element is 30 and I'll compare that with the target element. Yes, it is true. So I'll take count as 2 now. Count of 30 is 2 now. Again, go to the next element. Here 30 is equal to 30. True. Count is 3. Again go to the next element. 30 is equal to 30. Yes, count is 4. Next, we don't have any other elements to check. List ends here. So count is 4 now. Our target value, that is 30, appears 4 times in our given list. Let's take our target as 10. Then compare the target element with the first element of the list, that is 10. 10 is equal to 10. True. This condition becomes true. So I'll take count as 1. Then go to the next element. Here 10 is equal to 20. Target is 10 and element is 20. No. Next, go to next element. 10 is equal to 30. No. 10 is equal to 30. No. Next, 10 is equal to 30. No. Again, 10 is equal to 30. No. So, we don't have any other elements to check here. List ends here. So, count is 1. 10 appears only once in the given list. We can modify linear search algorithm like this to calculate how many times target appears in the given list. But as we know, it is better to use binary search when we are dealing with the large data sets. And also here, as mentioned in the problem statement, list is a sorted list. So let's see how to solve this problem using binary search algorithm. Okay, in binary search what we can do is, first we can find the first occurrence of that target element using binary search. Then find the last occurrence of that target element using binary search. Then you can find the count using this formula, last index minus first index plus 1. Okay, let me explain this with an example. First, what we need to do is, we need to find the first occurrence of the target element. So for example, 10 here. So 10 is occurred at 0th index. Then you need to find the last occurrence. Here last occurrence is also at 0th index. Because 10 appears only once, this is the first and last occurrence of 10 in this list, right? So first index is also 0, last index is also 0. Then how to calculate count? Here last index minus first index plus 1. Why plus 1? That is because index starts from 0, right? Here we need count. That's why we need to add plus 1 here. So 0 minus 0 plus 1. So we'll get count as 1. True, right? Here 10 appears only once. So count is 1. Next, let's take another example. Okay, let's take target as 30. First calculate the first occurrence of 30. Here in this list, first occurrence of 30 is at index 2. Then the last index. Find the last occurrence of 30. Last occurrence is at 5th index. First occurrence is at index 2. Last occurrence is at index 5. Now here let's calculate this. 5 minus 2 plus 1. 5 minus 2 is 3. 3 plus 1 is 4. So total count is 4. 1, 2, 3, 4. So using binary search, what we need to do is, first we need to calculate the first occurrence of the target element in the given list. We need to find the index. Then we need to find the index of the last occurrence of the target element in the given list. Then using this formula, that is last index minus first index plus 1, we can find the count. And how to find the first occurrence and last occurrence of the target element using binary search algorithm, we already discussed about this in the previous tutorial. So I'll give you the link of that in the description box. Alright, next let's write the program. Okay, here linear search. Let's modify this linear search algorithm first. Here in this linear search function, initially I'll take a variable count. Count is equal to 0. Let's go through the elements of the list one by one using for loop. Then compare the element of the list with the target element. Then here we don't want to return its index when target is found. We don't want to return its index. Instead of that, I'll take count is equal to count plus 1. I'll increment count and go to the next element. After searching entire list, then here we need to return count. Okay, so this linear search algorithm will find how many times target element appears in the list. Then here input is same, a list. Here we need a sorted list, remember that. Then a target element. Then here we'll call the linear search function. Here result is count, right? So if result is 0, then that means the target element is not present in the given list. So we can print that message. If it is not 0, then we can print here. Okay. Let's save this and execute this now. Let's take 5 elements. Let's enter the elements in the ascending order. Let's take 30. It appears 3 times. Let's enter 50. 50 appears 1 times. 5 is not found in this list. Okay, so this is how we can modify linear search algorithm to find how many times a target element appears in the given list. Next, let's talk about binary search algorithm. So in the binary search algorithm, what we need to do is first we need to find the first occurrence of the target element. Then we need to find the last occurrence of the target element in the given list. Then we need to use the count formula to find the count, right? So here initially let's change this function name. We'll use binary search but modified binary search. Here I'll just change the name to first occurrence. Alright. Then here what we need to do to find the first occurrence when target element is equal to middle element, we need to store that result. Let's take a variable answer equal to -1 initially. Then store the index and search in the left side. To search in the left side, I equal to mid -1. Here you need to return answer, right? Next here we need to find the last occurrence. So I'll copy this and let's define the function for last occurrence like this. Here let's change the function name to last occurrence. Here in the last occurrence, when target element is equal to middle element, we need to store the index and we need to search in the right side. So low equal to mid +1. Done. Okay, so this is first occurrence. Here last occurrence. Done. Next here for first index, call first occurrence. For the last index, last occurrence. Done, right? Call both these functions. We'll get first index and last index. Done. Next here I'll check first index is not -1. So when we find first occurrence and last occurrence, if the function first occurrence return -1, that means target is not found, right? That's why I'll use this condition. You can use last index is not equal to -1 also, because if target is not present in the given list, we'll get -1 as the value for first index and last index. Both this function will return -1, right? Here I'll take first index is not equal to -1. Then how many times? That is, let's calculate that. Count is equal to last index minus first index plus 1. This is the formula. Then here you can print count times. Okay, done. Let's save this and execute this. Let's enter 6 elements. Enter the numbers in the ascending order. Okay. Let's enter 20. 20 appears 4 times. Correct. 5. Let's enter not found scenario. 6 is not found. 10 appears 1 times. Okay, so this is how you can use binary search algorithm to find how many times the target element appears in the given list. Okay, so this is about count of occurrence problem. Next, let's talk about lower bound problem. Here is the problem statement. Given a sorted list and a target value, find the index of the first element that is greater than or equal to the target. If no such element exists, return size of the list. Here input is a sorted list which can contain duplicate elements and a target value. Output is first position where we can fit target. That is, we want first position where element is greater than or equal to target element. For example, if we take target as 30, here First element is 10. Compare 10 and target element. Here 10 is less than 30. So ignore. Next element is 20. 20 is less than 30. Ignore. Here next element is 20. 20 is less than 30. Ignore. Here next element is 30. And it is equal to target element, that is 30. So this is our output. Here this is the first position where element is equal to target element. We need to find the position where element is equal to or greater than the target element. If our target is 35, then here 10 and 35, 10 is smaller, 20 and 35, 20 is smaller, 20 and 35, 20 is smaller, 30 and 35, 30 is smaller, here also same, here also same, here also same, here 40 and 35, here this element is greater than 35. So this is our output. This is the first position where element is greater than or equal to target element. Here in this example, element is greater than target element. So our aim is to find the first position where element is greater than or equal to target element. Simple, right? To solve this problem, we'll use binary search algorithm, but normal binary search doesn't work here. We need to modify the binary search algorithm. Here we have normal binary search algorithm. In this, first we'll start by defining a search space. That is, we'll take two pointers, low and high. Low will point to the first element of the list and high will point to the last element of the list. Low equal to 0, high equal to length of list minus 1. Then we'll find the middle element. For that we'll use low plus high truncated division 2 formula. Then we'll compare the middle element and the target element. Here there are three possibilities. One is mid element is equal to target element. In that case we'll return the index. And the second scenario is mid element is less than target element. If middle element is less than target element, then we need to search in the right side, right? So we'll take low equal to mid plus 1. Third scenario, mid element is greater than target element. In that case, we need to search in the left side. So high will point to mid minus 1. To change the search space, we'll use low and high pointers. This is the logic behind the normal binary search algorithm. Now, we need to use this binary search algorithm to find the lower bound. If I take target as 30 here, then this is low, this is high. So we'll find the middle element. So middle element is this and target is 30, right? When we compare target and middle element, here target is equal to middle element. In that case, in the normal binary search, we'll return its index, that is 3. So we'll get output as 3. But here, the first position where element is greater than or equal to target element is second position. So we need to get output as 2. But here we'll get output as 3, right? That's why normal binary search doesn't work here. So what we need to do is, first we need to start by looking at the entire list. Take the entire list. Find the middle element of the list. If the middle element is smaller than the target, ignore left half and continue searching the right half. And if middle value is greater than or equal to the target, keep this position as possible answer and continue searching the left half. This process continues until there is only one possible position left, and that position is returned as lower bound, which is the index of the first number greater than or equal to target. Let's take examples. Okay, if target is 30 and this is a list, we want to find where we can place this 30 in this sorted list. Here output is in the fourth index, right? Here we can see 10, 20, 20, 20. These are all smaller number, and here 30 is equal to 30. This is the first position where we can place our target. So output is index 4. In the lower bound, if target is already present in the given sorted list, we'll search for the first occurrence, okay? Okay, next let's apply modified binary search algorithm and see how this algorithm works to find lower bound index. Okay, so here we have list, target is 30. Initially low will point to the first index, and in normal binary search, high will point to last value. But here high will point to length of list. That is, here we'll take low equal to 0, high as length of list, here 8. In normal binary search, we'll take high as length of list minus 1. That is the last index of the list. But here we need to take high is equal to length of list. Why? Because here we are finding the position to place the target element in the sorted list. That position can be at the beginning, between elements, or after the last element. For example, if target is 80 here, So we need to place 80 in the last index after this 50 because 80 is greater than all other elements here. So we need to place that at last. So to place that, we need this position, right? So that's why here we need to take high as length of list. Okay, next we need to find the middle element. Here low plus high truncated division 2 to find the middle. 0 plus 8 truncated division 2, so we'll get this as middle. Then compare this middle element with the target element. Here middle element is equal to target element. If the middle value is greater than or equal to the target, then we need to keep that position as possible answer and we need to continue search in the left half. Here it is equal, so we need to continue search in the left half and we need to take this position as possible answer. That's why we need to take high equal to mid. So now this is a search area. Now again find mid. 0 plus 4 truncated division 2, so we'll get this as middle element. Compare middle element with the target element. 20 is equal to 30. 20 is less than target here. When 20 is less than target, then we need to ignore left half. We need to search in the right half. So here low becomes this one, right? Low points to this one now, mid plus 1. So now this is a search area. So find the middle element. Here we'll get this as middle element. 3 plus 4 truncated division 2, so we'll get 3. Then compare this element with the target. 20 is equal to 30. No, it is not. 20 is not equal to 30. Actually 20 is less than 30. So we need to take low equal to mid plus 1. So now low will point to here. Now actually in this search area we have only one element, that is our possible answer. Here in the modified binary search, when low is equal to high, we need to stop the search. And here this is our possible answer. So here you can written low. Low will contain our possible answer. That is output is 4th index. We can place target 30 in this 4th index without disturbing the sorting order. Let's take another example. Let's take 35. Here we can see 35 is not present in this list. So if you want to place 35, where will you place that? Here, right, in the index 6. So we'll get list as 10, 20, 20, 20, 30, 30, 35, 40, 50. So we need to get output as 6. Next, let's use modified binary search algorithm on this example and we'll see whether we'll get right answer or not. So initially, low will point to this, high will point to 8, length of list here. Then target is 35. Find the middle element, low plus high truncated division 2, so we'll get 4. Compare 30 and 35. Here target is greater than middle element. So we need to ignore the left half and continue search in the right half. So to search in the right half, I need to take low as mid plus 1. Now this is our search area. Find the middle element. 5 plus 8, that is 13. 13 truncated division 2, so we'll get this as middle element. Compare 40 and 35. Middle element is greater than target here. So when middle element is greater than or equal to target, we need to take this as the possible answer and we need to search in the left half, right? We need to take high equal to mid. Now this is our high. 30 and 40. Find the middle element. 5 plus 6 truncated division 2, so we'll get 5. This as the middle element. Compare 30 and 35. Middle element is smaller. When middle element is smaller, we need to search in the right half, right? So here low equal to mid plus 1. So now here you can see low is equal to high. Only one element is present here. So this is the possible answer. Written low now. Low value is 6. That is our answer. At 6th position, 6th index, you can place 35. Okay. Here in the normal binary search, we'll find the target value in the sorted list. Find the first position where value is greater than or equal to target. Written -1 if target doesn't exist. Works even if target is not present. If target is not present, then also we'll get an index. If duplicates present, returns any index of the target. Here find first occurrence in case of duplicates. Here we'll take low equal to 0, high equal to length of list -1. Here low equal to 0, high equal to length of list. Because here we'll search for our target element. Here we are searching for the position. This is the stopping condition. When mid element is equal to target or low becomes greater than high, we need to stop normal binary search. But here when low becomes equal to high, we need to stop. Okay, so this is the difference between normal binary search and modified binary search. Next, let's write the program. Here, input is a sorted list as well as a target element. So here we can see the code for that. Here, I'll assume that you're already familiar with how binary search algorithm works. So I won't explain the terms related to binary search algorithm in more detail. So next, here let's define the function for modified binary search. I'll take lower bound. Here, a list and target, just like we do in the normal binary search. Low equal to 0, 2 pointers, high equal to length of list. Then in the binary search, we'll use while loop and we'll take while low is less than or equal to high. But here, we need to stop when low becomes equal to high. So when low is less than high, we'll perform these operations. When low becomes equal to high, we need to stop. Here, find the middle. Low plus high truncated division 2. Then we need to compare middle element. So numbers made is less than target. Look, if target is greater than the middle element, then we need to search in the right side, right? We need to take low equal to mid plus 1. This is how we will search in the binary search algorithm also, right? If target is greater than the middle element, we'll search in the right half. Else, if middle element is equal to target element or target is smaller than the middle element, then we need to search in the left half. Also, what we need to do is, we need to take the middle index as one of the possible answer. That's why here, we need to take high is equal to mid. In the normal binary search, we'll take high is equal to mid minus 1. But here, we need to include this target is equal to middle element condition also here in this else block. That's why we need to take high equal to mid. We need to take that index as one of the possible answer. Okay, so we need to take high equal to mid. Then here, after while loop, when low becomes equal to high, we need to return low. Here you can return high also because this condition will stop when low is equal to high. So both low and high point to the same index. Here I'll return low. Now we are done. Here we need to call this function and store that result because this function will return a result, right? Next, print the result, save and execute. Number of elements in the list, let's enter 5. Then I'll enter 35. We can place this 35 after this 30, right? Before 40. So index is 0, 1, 2, 3. We need to get index as 3. Yes. I'll enter 40. So we'll get lower bound index as 3. Okay, so this is the one of the way to solve this problem. Next, let's talk about another method, that is the classic method where we'll store the index and we'll continue search in the left side. So start by defining your search space. Take low and high pointer. Low equal to 0, high equal to length of list minus 1. Then find the middle element. Low plus high truncated division 2, use the same formula. Then compare middle element and target element. Here we need to consider only two possibilities. Because here we want to find the first position where element is greater than or equal to target element. So here we need to consider only two possibilities. Mid element is less than target and mid element is greater than or equal to target. So when mid element is less than target, if element is less than target, we need to ignore that, right? So here when middle element is less than target, we need to ignore the left side and we need to search in the right side. To search in the right side, we need to take low equal to mid plus 1. Why ignore all the elements in the left side of the middle element? That is because here numbers are sorted in ascending order. If middle element is less than target element, that means all the elements present in the left side is also smaller than the target element. So no need to check them. Simple, right? Next, let's consider next scenario. What if mid element is greater than or equal to target element? Here we want to find the position where element is greater than or equal to target element. When this condition is true, that means we found an element which is greater than or equal to target element. So now we found our answer. So what we can do is we can save that answer. Take a variable, for example answer, then store that index. Now we found our answer, we need to stop, right? No, because here we found a position where element is greater than or equal to target element. But here in the lower bound, we want to find the first position where element is greater than or equal to target element. Here we found a position where element is greater than or equal to target element. Whether this one is the first position, we don't know. So what we need to do is we need to continue search in the left side. To search in the left side, we need to take high equal to mid minus 1. When the middle element is greater than or equal to the target, we store the index because it satisfies the lower bound condition. A element greater than or equal to target element. So it can be one of the possible answer. However, we can't stop here. Binary search doesn't check elements sequentially. Even though we found a position where element is greater than or equal to target, we do not know whether this is the first such position. There might be another element on the left side that is also greater than or equal to target element. Here we need to find the first position where element is greater than or equal to target element, not any position where element is greater than or equal to target element. That's why when we found a position where element is greater than or equal to target element, save that answer. It can be one of the possible answer and search in the left side. Why left side? Because if I want to search for the first occurrence or first positions, we need to search in the left side. Because here numbers are sorted in ascending order. So this is the modified version of binary search algorithm to solve lower bound problem. In the previous part, we modified binary search algorithm to solve lower bound problem. We can call it as version 1 and this algorithm as version 2. What is the difference between previous version and this one? Okay, so in the first version, we can call it as boundary method. Instead of storing answer, we shrink the search space until low itself becomes the lower bound. But in the second version, we can call it as store answer method. Here, whenever we find a element which is greater than or equal to target element, we'll store that index as one of the possible answer and move left to check if there is an earlier valid position. First version, in the previous version, we won't take any variable to store the result, but here we'll use a variable to store the result. And in the previous version, initially we'll take high equal to length of list. Here we'll take high equal to length of list minus 1. That is because in the previous version, by setting high equal to length of list, we can handle the case where all elements greater than target element gracefully. But here, this version stores the possible answer in a separate variable. So high only needs to cover actual indices of the list. There is no need to go past the last element because answer handles the case when target element is greater than all other elements in the list. And also stopping condition is also different. Here in the first version, when we have only one element in the search space, we need to stop. But here when low becomes greater than high, we need to stop. This second version is more similar to normal binary search algorithm. Okay, so let's take few examples. First, let's take target as 20 and find the middle element. Here, this is the middle. Compare the middle element and target element. Here, middle element is greater than target element. When we found an element greater than or equal to target, what we need to do is we need to store this index. So take a variable and store this index and search in the left side. So here, high need to point to this side. We can ignore these elements now. This is a search space. Now find the middle element. This is middle element. Compare middle element and target element. Middle element is equal to target element. When element is greater than or equal to target element, save the index and search in the left side. So here answer becomes 1. High equal to mid minus 1. Calculate middle. So here 10 and 20. Here 10 is smaller. Here middle element is less than target element. When middle element is less than target element, we need to search in the right side. So low becomes mid plus 1. Now here you can see low is greater than high. In this binary search algorithm, when low becomes greater than high, we need to stop. So this is our answer. Here we need to find the first position where element is greater than or equal to target element. Here 20 is equal to 20 and it is present at index 1. That is our output. Okay, let me take another example. Let's take 50. Okay, so this is low and this is high. Here you can see 50 is greater than all the elements present in the list, right? Initially what we'll do is we'll take this answer as 8. That is length of list. Then find the middle element. 30 is equal to 50. No, 30 is smaller than 50. If element is less than the target element, search in the right side. Low becomes mid plus 1. This is a search area now. Find the middle element. Compare middle element and target. Here element is less than target element. So search in the right side. Now again find the middle element. Now find the middle element. 30 is less than 50. So search in the right side. Find the middle element. 40 is less than 50. So low becomes mid plus 1. Search in the right side. So now here you can see low is greater than high. So now we need to stop. So we'll return this answer as 8. As I said, in this version, to handle this scenario when target is greater than all other elements in the list, we'll use this method. Here we use an answer variable to store the possible lower bound index at each step of binary search. We initialize this variable with the default value, that is length of list, because the lower bound represents an insertion position, not necessarily an existing index. If the target is greater than all the elements in the list, then middle element is less than target condition will be true for every mid. In that case, the condition middle element is greater than or equal to target never becomes true. So answer equal to mid is never executed. Without a default value, answer would remain undefined or incorrect. So by initializing answer equal to length of list, we correctly return the position after the last element, which is the valid lower bound. Here, if we didn't initialize answer as length of list, here we saw the statement answer equal to mid never executes. So we won't get proper answer. So that's why initially we need to assign length of list as the default value for this variable. Okay, next example. Target is 25. Initially we'll take this value as 8, that is length of list. Now find the middle element. Compare the middle element 30 and 25. Here 30 is greater than 25. Here we found a position where element is greater than target element. So it can be one of the possible answers. So save the index. Now answer becomes 3. We'll update this variable. Now answer is 3. We need to search in the left side. High is mid minus 1. This is our search area now. Find the middle element. Then compare 20 and 25. Here 20 is smaller. If element is smaller, then search in the right side. So low becomes mid plus 1. Now this is our search area. Find the middle element. Compare 20 and 25. 20 is smaller. So search in the right side. Low becomes mid plus 1. So now here you can see low is greater than high. We need to stop binary search. So this is our answer. Here at index 3, we have an element which is greater than 25 here. That is our target. Okay, next let's write the program. Here we have a normal binary search algorithm. Here you can see the program. Next, let's modify this algorithm. Low equal to 0, high equal to length of numbers minus 1. Low is less than or equal to high. Find middle. And if middle element is equal to target, here we have this condition. We don't want this. We can remove this. Here, if middle element is less than target element, if element is less than target element, then we need to ignore left side. We need to search in the right side. So low equal to mid plus 1. Else, this will execute only when numbers of mid is equal to target or numbers of mid, that is mid element is greater than target element. In this case, we need to store the mid element also. So we'll take answer equal to mid, and initially I'll take its value as length of list. To find the length of list, we'll use len. If middle element is less than target element, then I'll take low equal to mid plus 1. Search in the right side. Else, when this else becomes true, when middle element is greater than target or when middle element is equal to target element. What we need to do at that time? We need to store that index first. It can be one of the possible answer. Then we need to search in the left side. Why left side? Because here we want first position where element is greater than or equal to target element. To search for that first position, we need to search in the left side. Next, here we need to return answer. Why answer? Because it will hold a final answer. Then here, this function will return answer. Then we can just print that without using if else. I'll print like this. Lower bound index and result. Save and execute. Be careful about the indentation, okay? Let's enter 5. lower bound index is at 2. Let me enter 30. So at index 3. If I enter 6, we'll get lower bound index as 5. Okay, so this is how we can solve the lower bound problem using binary search algorithm. Next, let's talk about upper bound problem. Here is the problem statement. Given a sorted list and a target value, find the index of the first element that is strictly greater than the target. Here input is a sorted list and a target element, and output is index of the first element that is strictly greater than the target. Here we have an example, sorted list and target element. Here output is 5. For example, if I take target as 30, then here output is 7th index. That is, when target is 30, we need to ignore all the numbers smaller than or equal to the target element. Here 10 is smaller than 30, 20 is smaller than 30, 30 is equal to 30. So we need to ignore all the numbers which are smaller than or equal to the target element. Then here 40 is greater than 30. This is the first position where element is strictly greater than the target element. So this is our output. If target is 25, here 10 is smaller than 25, 20 is smaller than 25, 30 is greater than 25. This is the first position in this sorted list where element is greater than the target element. So this is our upper bound index. To solve this problem, I'll use binary search algorithm, but here we'll modify the binary search algorithm. Start by looking at the entire list. Find the middle element of the list. If the middle element is less than or equal to the target, ignore left half and continue searching the right half. If the middle value is greater than the target, keep this position as possible answer and continue search in the left half. This process continues until there is only one possible position left. That position is returned as the upper bound, which is the index of the first number greater than the target. So we need to use this algorithm now. In the previous tutorial, we talked about lower bound problem. The difference between upper bound and lower bound is, in the upper bound, we'll find the first position where a number greater than the target can appear. Here, we'll find the first position where target can appear. Here you can see the difference between upper bound and lower bound with an example. Alright, next, let's take an example. Here we have a list. Target, let's take target as 30. Then in the binary search algorithm, we'll take two pointers, low and high. Low will point to the first element and high will point to the last element. But in the upper bound, high will point to length of list. That is, here we'll take low equal to 0, high as length of list. That is because here we are finding the position, right? If our target is 60, where you will place this 60 in this list? Here in the 8th position, right? Because 60 is greater than all these elements. What is the output when target is 60? That is 8th position. To get that, we need to take high as length of list. Both lower bound and upper bound are about finding a position. That position can be at the beginning, between elements, or after the last element. So algorithm must allow searching one position beyond the last index. That's why we'll take high as length of list here. Alright, next we need to find the middle element. So low plus high truncated division 2, we'll get here 4 as middle element. Formula is say mid equal to low plus high truncated division 2. 0 plus 8 truncated division 2, that is 4. So we'll get this as our middle element. Now we need to compare the middle element and target element. If middle value is less than or equal to the target element, then we need to ignore the left part and we need to search in the right part. Here middle element is equal to target element here. So we need to search in the right side. Low becomes mid plus 1. So now this is our search area. Find the middle element. 5 plus 8, that is 13. 13 by 2. So this is our middle element. Compare the middle element with the target element. 40 is equal to 30. Here 40, that is middle element, is greater than 30. When middle element is greater than 30, what we need to do is we need to keep this position as well as we need to search in the left side. So we'll take high equal to mid. So this will become my high now. Now this is our search area. Find the middle element. 5 plus 6 truncated division 2, 5. Compare the middle element and target element. Here, middle element is equal to target element. When middle element is less than or equal to target element, we need to ignore the left part and we need to search in the right side, right? So here, low becomes mid plus 1. Now low will point to here. According to the algorithm, when we have only one element, that is when low becomes equal to high, we need to stop the search. So here, this remaining position 6 is our output. We can place this 30 in this sorted list at index 6. So you can see the difference between lower bound and upper bound here. According to the lower bound, we can place our target 30 here in the 4th index. But here in the upper bound, the output is at index 6. Now let's take another example. Let's take 35 as our target. Compare middle element and target element. Here target is greater than the middle element. Middle element is less than the target element. When middle element is less than or equal to target element, we need to search in the right side, right? So low becomes mid plus 1 here. Okay, this is our search area. So again find the middle. Compare the middle element and target. Here middle element is greater than the target. Middle value is greater than the target, then we need to keep that position and we need to search in the left side. Here, so mid becomes high. Now again find the middle. This is middle. Compare middle and target. Here, middle element is less than target element. When middle element is less than target element, so we need to search in the right side, right? So low becomes mid plus 1. Now only one element is present here. Low is equal to high. Now we need to stop and output is 6th index. We can place 35 in the 6th index. Let's take 5 as our target. Compare 30 and 5. Here target is smaller, middle element is greater. Keep this position and search in the left side. So this becomes high. This is our search area now. Find the middle element, 4 truncated division 2. So this is middle. Compare middle and target. Here 20 is greater. When 20 is greater, keep this position and search in the left side. This becomes high now. Now again find the middle element, 20 and 5. Here middle element is greater than target now. So when middle element is greater than target, keep that position and search in the left side. Calculate middle. This is middle, 10 and 5. Again 10 is greater than 5. When 10 is greater than 5, we need to take middle as high and we need to search in the left side, right? Now low is equal to high, we need to stop and this index is our output. So you can written low. So 0th index. You can place target 5 at 0th index. Okay, next let's write the program. Here we have a lower bound program. I'll give you the link of this video in the description box. Today let's write upper bound program. Input is same, a sorted list and a target element. Here let's define upper bound function. So function name is upper bound, numbers and target, then low equal to 0, high equal to length of numbers. While loop condition, low is less than high. When low becomes equal to high, we need to stop. Inside the loop, mid, low plus high truncated division 2. Here, when middle element is less than or equal to target. In the upper bound, when middle element is less than or equal to target, we need to ignore the left side and we need to search in the right side. That's why we need to include this condition here. Low is equal to mid plus 1. That is, we need to search in the right side. Here else, high equal to mid. When middle element is greater than the target element, we need to take that position as possible answer and we need to search in the left side. That's why I need to take high equal to mid. In the lower bound, we'll use less than symbol. Here in the upper bound, here you need to use less than or equal to. That is the difference. Then here you need to written low. Low becomes equal to high. This condition becomes false, so control will come here. Low and high both points to the answer. You can take written low or written high. I'll take written low. Alright. Then here we need to call this function upper bound. And here we need to print upper bound index. And we are done. Let's save this and execute this. Let's enter target element as 30. In the lower bound, we'll get index as 2, but here we'll get index as 3. Okay, so this is the first way to solve this problem. We can solve this using another method. This method is more simpler and more similar to normal binary search algorithm. Here we want to find the first position where element is strictly greater than the target element. For that, what we need to do is, first step, start by defining your search space. So we'll take low equal to 0, high equal to length of list minus 1. That is, we'll point low to the first element and high to the last element of the list. Same as normal binary search. Then we'll find the middle element. We'll use the same formula, low plus high truncated division 2. Then we'll compare the middle element and target element. Here we need to consider only two possibilities. One is when element is smaller than or equal to the target element. Another one is when element is greater than target element. Here, if elements are smaller than or equal to the target element, we need to ignore them, right? Here we want to find the first position where element is greater than the target element. So, the elements which are smaller than or equal to the target elements are ignored here. If middle element is less than or equal to target element, that means all the elements present in the left side of the middle element is also less than or equal to the target element. Because here input is a sorted list. We are using list where numbers are sorted in ascending order. So here we need to ignore all the smaller number or numbers equal to the target element. So that's why when middle element is less than or equal to target element, we need to search in the right side. For that, we need to take pointer low equal to mid plus 1. If middle element is less than or equal to target element, just ignore them. So search in the right side. Okay, so the next case is when middle element is greater than target element. So what we need to do when middle element is greater than target element? Here our aim is to find the element which are strictly greater than the target element, right? Here we found an element which is greater than target element. So it can be one of our possible answer. Why it is one of the possible answer? Because here we are not searching the elements in the sequential order. We are using binary search algorithm. Because of that, we don't know this element is the very first element where element is greater than the target element. Here we got a position where element is greater than the target element. Whether this one is the first position, we don't know. In the upper bound problem, we want to find the first position where element is greater than the target element. So to find that, we need to continue search in the left side. Why left side? That is because if I want first position or first occurrence, we need to search in the left side in the sorted list. Okay. So here first take a variable and store this index. Index is here mid. Okay. Continue search in the left side. So for that you need to take high equal to mid minus 1. Why save the index? Because here we found an element which is greater than the target element. So it can be one of the possible answer. Then why search in the left side? Because we found an element which is greater than the target element, but we don't know that is the first element in the list where element is greater than the target element. Here we want first position where element is greater than the target element. To find that first position, we need to continue search in the left side. Let's take an example. Let's take target as 25. First, let's define the search space low and high. Then find the middle element. So here this is mid index, that is 3, and this is middle element. Now compare the middle element and target element. Here element is greater than the target element. Now we found an element which is greater than the target element. Now what we need to do? This index can be one of the possible answer, right? Because here element is greater than the target element. So I'll store that index. Take a variable and store that index. Now next, we need to continue search in the left side. Here now high equal to mid minus 1. This is our high. This is our search area now. Then again apply modified binary search algorithm. Here low plus high truncated division 2. So this is our mid. Compare mid and target element. Here element is less than the target element. When element is less than target element, we need to ignore that element. So we need to search in the right side of the middle element. So low equal to mid plus 1. So now this is our search area. Find the middle element. Low plus high truncated division 2. So we'll get this. Compare 20 and 25. Here 20 is smaller than the 25. So what we need to do? We need to search in the right side of the middle element. Low becomes mid plus 1. Now here you can see low is greater than high. In the binary search algorithm, when low is greater than high, we need to stop. So we got answer as 3. Let me take 15. This is low, this is high. Find the middle element. Compare the middle element and target. Here this element is greater than the target element, one of the possible answers. So store the index. Then search in the left side. Find the middle element. 20 and 15. 20 is greater than 15 now. This can be the first position where element is strictly greater than the target element. So store this index now. We don't want previous index. Store this latest index now. Answer is 1. And continue search in the left side. So here this becomes high. Again find the middle element. 10 and 15. Here 10 is smaller. Element is smaller, so search in the right side. Low is mid plus 1. Now here low is greater than high. When low is greater than high, we need to stop. This is our answer. Let's take target as 30. This is mid. Compare middle element and target element. It is equal. When element is smaller than or equal to middle element, we need to ignore left side and we need to search in the right side. So here low becomes mid plus 1. So now this is our search area. Find the middle element. This is middle element, right? 30 and 30 equal. So search in the right side. Now find the middle element. 30 and 30 equal. So search in the right side. Low equal to mid plus 1. Find middle element. 40 is greater than 30. So we need to take this as one of the possible answer. So store that index and search in the left side. To search in the left side, we need to take high equal to mid minus 1. So now here you can see low is greater than high. We need to stop. This is our answer. Now what about target as 50, which is greater than all the elements in this list? Here mid element and target element. Middle element is smaller, so search in the right side. Middle element and target element. Here middle element is smaller, so search in the right side. Again find the middle element. Middle element and target. Here element is smaller than the target, so search in the right side. Again middle element and target. Here target is greater, so search in the right side. So here low equal to mid plus 1. Now here you can see low is greater than high. What to do in this situation? Here whenever middle element becomes greater than the target element, we'll store that index in a variable, right? So initially I'll take its value as length of list. Default value for this variable is length of list. So here in this situation you can see in every comparison element is smaller than the target element. So answer equal to mid is never executed. That's why we'll take default value for this variable, that is length of list. Here length of list is 8. So we'll get 8 in this situation. So upper bound index for target 50 in this list is 8th index. To solve this scenario gracefully, we'll take default value for this variable as length of list. If we found a position where element is strictly greater than the target element, then we'll replace this value. We'll upgrade this value. So this is about example. Next, let's write the program. Okay, here we have a lower bound program. Now we want to write upper bound program. I'll keep the function name as binary search. You can take upper bound also. Low equal to 0, high equal to length of numbers minus 1. This is the 2 pointers to define search space. Next here we'll take a variable to save the index of the element when element is strictly greater than the target element. Initially I'll take its value as length of numbers. Then low is less than or equal to high. This is the loop condition for normal binary search. Then find the middle element. Then compare numbers of mid is less than or equal to target element. If middle element is less than or equal to target element, ignore those elements, search in the right side. That's why low equal to mid plus 1. Else. Here else part will execute when middle element is strictly greater than the target element. That time what we need to do? We need to save that index and we need to search in the left side. And lastly we need to return answer. Okay, next here inputs, target, and we need to call the binary search. It is for upper bound. Here we need to take a variable to store the result and here we need to print upper bound index. Save and execute. Let's take 5 elements, numbers in ascending order. Let's enter 60. So 5. Enter 6. Let's enter 2. Index 3. Okay. So this is how we can solve upper bound problem using another method. Okay, so this is how we can solve lower bound and upper bound problems. Next, using this lower bound index and upper bound index, we can calculate the count of occurrences. That is, counting the number of occurrences of a number in a sorted list. So example, in this list, if I take target as 30, it appears 4 times. If I take target as 20, it appears only once. If I take target as 10, it appears only once. Okay, so how to find count of occurrence using lower bound and upper bound index? Here we need to find the upper bound index of target. So here target is 30. Upper bound index of 30 is 6. Then here lower bound index, that is 2. Then we need to use the formula count is equal to upper bound minus lower bound. So 6 minus 2, that is 4 times. Okay, here upper bound index is the first position where element is strictly greater than the target element. In this example, 10, 20, 30 are less than or equal to target element. That's why the 6th index is the upper bound index here. For the lower bound, we need to find the first position where element is greater than or equal to the target element. Here at index 2, 30 is equal to 30. So that is the first position. So lower bound index is 2. 6 minus 2 will get 4. Correct, right? Count is 4. So now here you can see another example. If we take target as 20, here to find the count of 20, we need to find upper bound index and lower bound index of 20. Here upper bound is index 4. This is the position where element is strictly greater than the target element. Then here lower bound index, we need to find the first position where element is greater than or equal to the target element. Here this is the first position, right? Here element is equal to target element. So 1. Now 4 minus 1 will get count, that is 3. So 20 appears 3 times in this example. If target is 30, upper bound is 6 and lower bound is 4. So 6 minus 4, 2. 30 appears 2 times. Okay, now why this lower bound and upper bound works? That is because here list is sorted. When list is sorted, all the duplicate appears together next to each other, right? So by finding upper bound and lower bound, we can calculate count easily. Upper bound is the first index greater than the target element and lower bound is the first index of the target element. So when we minus lower bound from the upper bound, we'll get the count. And also if an element is not present, for example, if I take target as 50 here, I want to find the count of occurrence of 50, then here you can see upper bound is 7th index, lower bound is also 7th index, 7 minus 7, 0. So we'll get count as 0. To find the count, we need to first find the upper bound index and lower bound index of the target element. Then by using the formula upper bound minus lower bound, we can calculate the count easily. Alright, next let's write the program. Okay, so here we have upper bound program. Okay, first let's define 2 functions. One is for lower bound, another one is for upper bound. We'll calculate upper bound and lower bound. Then using the formula upper bound minus lower bound, we'll calculate the count. So here this is upper bound. So upper, let's take function name like this, okay? So here you can see the condition less than or equal to the target, then low equal to mid plus 1. This is upper bound program. Before that, let's define a function for lower bound. Take function name as lower bound and here difference is only this symbol. If middle element is less than target element, search in the right side. Otherwise, save the index and search in the left side. This is lower bound. Here in the upper bound, when middle element is less than or equal to the target element, search in the right side. Otherwise, save the index and search in the left side. Right? Next, we need to call upper bound and lower bound function. So here, upper index as the variable name. You can take any variable name, okay, suitable variable name. Here upper bound, let's call upper bound function first. Then calculate lower index, that is lower bound index. I'll call lower bound function name. Here you can see lower bound and upper bound. We'll call these two functions to find upper bound and lower bound of the target element. Next here, we need to use the formula count is equal to upper bound minus lower bound, upper index minus lower index here. Done. Then we need to print that and we are done. Let's save this and execute this. Let's enter 5 elements. 1, 2, 2, 3, 4. Let's enter 2. So count of 2 is 2. It appears 2 times. Let's enter an element which is not present in the given list of numbers. So count is 0. So let's take 40. 40 appears 1 time. Okay, so this is how we can find the count of occurrence of the target element using upper bound index and lower bound index of that target element. So that's it for now guys. Thank you for watching. Don't forget to subscribe to my channel. I will meet you in next class. Till then, take care.